Hello, this is Abdullah Alenzi. I am a PhD student at the Department of Computer and Science and Engineering in the University of North Texas. Presenting my paper with title Element-Based Test Suite Reduction for SARSA-Generated Test Suites on behalf of my colleagues Waleed Alhumud and Dr. Renee Bryce. Let's move to the agenda. I will start with the introduction, then the motivation behind this study. Then I will go over some terminology and definition in the context of our study. Then we will present our proposed algorithm element-based criteria. Then after that, we'll go for the methodology and the outcomes of this study, and finally the conclusion. Let's move to the introduction. Android is widely used and it is the most popular platform that has the largest market share among mobile devices. In the smartphone industry, it's considered as the most extensively utilized operating system. Recent statistics indicate that Android has become the favorite option with over 2 billion active devices globally, and it has more than 74 of market share. In general, the environment of mobile apps depends on interaction of the user utilizing touchscreen and other sensors, making testing these apps a challenge. The Android apps operate in a fast changing environment where there is a large benefit to increasing the efficiency and effectiveness of app development and testing. Various factors making testing mobile apps expensive, such as the interactive nature of the user interface of these apps, the considerable required time to develop the test cases of user interface, security, and running on different devices. Thus, it's essential and important to employ efficient and cost-effective testing techniques and tools. In automation testing, reinforcement learning has made its way in test case generation, and it's proven its ability to produce efficient test cases. Although reinforcement learning algorithms have shown a promise for automated test generation, they often contain redundant test cases. Thus, it opens doors for enhancement and improvement, since running all test cases is costly and time consuming. In this study, we seek to address this problem of redundancy by applying a hybrid approach that combines test suite reduction with reinforcement learning based on elements for 5 open source Android applications, and conducting an empirical study that reveals the value of the new hybrid approach direction. Let's move to the motivation behind this research. Given the popularity and the tremendous usage of Android apps and testing cost, it's crucial to create efficient and cost-effective testing tools to mitigate this expense. Catching and fixing errors or adding new features, improving current feature are regular activities in the development process of application. Through these processes, additional and redundant test cases are added into the original test suites, which makes performing regression testing expensive. Also, Automated test generation with reinforcement learning algorithms have shown a promise. However, there is a potential opportunity to improve as these algorithms often produce test suites with redundant coverage. The execution of redundant test cases significantly takes a considerable time and effort, resulting in costly testing activities. Finding tuning of reinforcement learning parameters is a time-consuming also solution because it requires a consideration of the characteristics of the application under test and its environment. Let's move. Before we going into depth, let's us define some used terminologies and definition in the context of this study. A test suite consists of a collection of test cases which are used for software testing, and each test case has one or more events. Test suite reduction, it is the process to remove redundant and unnecessary test cases that do not contribute to the coverage requirement. Action, as you see here, it's the individual user action such as click, touch, or long click. The element, it is a user interface widget that the action is executed on, such as the button, image, text field, which is in this case it's our major component that we depend on to remove redundant test cases in this study. So we use element-based criteria. Where the event, as you see here, represent the combination between action and element. In our previous study, we used events to reduce test suites utilizing event-based criterion. Let's take this example to explain the element, action, and event using a recorder application. A user click a new record button, and this click is an action, while the new record button is the element. The event, as you see here, combines the action and the element. So it will be clicks and a new record. Now, my colleague Waleed will go over the rest of this presentation.
This slide explains the used criterion in this study, which is element-based criterion. Depending on elements, the element-based criterion ELBC reduced the size of the test suite based on a greedy approach by producing a minimal subset that represents the entire test suite and meets all requirements following HGS approach. This set is called the representative set, RS. To make the idea more clear, let's take an example. Assume a test suite that has 5 test cases, and based on a greedy mechanism, identifying the largest test case, which is test case 1, as you can see here, due to its inclusion of the highest number of elements. We have 5 elements. Depending on elements, it's noted that the subset test cases of test case 1 are test case 2 and test case 3 and test case 4, because they all have the same elements in test case 1. And the redundant test cases is test case 4 because it's identical to test case 2. So to identify the smallest subset of test suite that guides to determine the RS, ELBC eliminates redundant and subset test cases. So the representative set in this example is test case 1 and test case 5 that represent the reduced test suite. This slide shows an example that determines briefly how our previous criterion, event-based criterion in a previous study, and the current criterion, which is element-based criterion, reduce test suites. Event-based criterion, EBC, depends on events of Android to reduce the suite, while element-based criterion, ELBC, relies on elements of the Android test suite to reduce the test suite. Suppose a test suite that has 4 test cases, and each test case has events that are composed of combination of elements and action. The events in test case 3 and test case 4 are part of test case 1. Thus, test case 3 and test case 4 will be removed, and following the mechanism of EBC, test case 3 and test case 4 are removed from the test suite, as I said, and the reduced suite RT will be contains only test case 1 and test case 2, which represent only 50% of the original test suite. In case of applying ELBC, test case 2 and test case 4 both are redundant and subset of test case 1. Additionally, test case 3 has the same element in test case 1, EL1, EL2, and EL5. And therefore, the test cases 2, 3, and 4 will be deleted, and the output of ELBC will be just only test case 1, which represent only 25% of the reduced suites. Let's move to the an overview of the test suite reduction process in this study. In the first step, we use a test suite that generated by a reinforcement learning algorithm in a previous study titled Android GUI Test Generation with SARSA by Khurram Khan. Then we calculate the code coverage before the reduction of the test suites. After that, we'll apply our algorithm using element-based criterion to reduce original test suite. And the output of this process is the reduced test suites. So to evaluate and validate our results, we compare the test suite before and after reduction in regards to the size, as well as we measure the code coverage for the reduced suite to be compared with the original test suite. Here is the reduction algorithm in this research. The input of this algorithm is Android suite that generated by SARSA, and the output is the representative set following this algorithm. The proposed algorithm relies on identifying the largest test case in the test suite that has the maximum number of elements until all test cases are covered, inspired by a greedy algorithm. As you can see it here in line 5, it sorts the test cases of the original test suites, descending based on the number of elements, and if there is a tie between test cases, the selection will be randomly. It compares the first test case, which is the largest one, with all other test cases, and if there is subset or equal of the test case, it will be removed as shown in line from 6 to 10. This comparative process down the remaining test cases until all equivalent and subset test cases have been discarded, and to return the representative set in this process. Let's move to the methodology. This slide shows the experimental setup of this study to observe whether ELBC can potentially reduce test suite generated by reinforcement learning, SARSA, for each software under test, and to what level maintain the code coverage. First, we conduct an empirical evaluation on test suite of 5 open source Android applications that are different in size and functionalities. And the characteristic of these applications, including the line of code and the methods and classes, all this information can be seen in this table. Also, in this study, we use 2 evaluation metrics to validate our results. The first one is to measure the percentage of the reduction size of the reduced suite by comparing the size of the original suite and the reduced suite based on this equation that calculates the percentage of reduction, where T is the original test suite and T prime is the reduced test suite. The second metric is code coverage, to obtain the code coverage of all test suites before and after reduction. And code coverage is considered as a common metric used by testers to measure which part of the source code has been executed by the test suite in our study. In our study also, we used line, method, and class as the utilized coverage matrix. We also used Jakuku, which is an open source tool, to obtain the code coverage. Let's talk about the test suite, the generated test suite that used in this study. Test cases of the 5 Android applications in this study have been generated based on the reward estimation and learning mechanism of the SARSA algorithm, state action, reward, state action. SARSA is a model-free reinforcement learning algorithm that applies a trial and error approach to dynamically learn from the environment, which is GUI of Android application in our case, as shown in this figure. To generate a test case, it relies on selecting events in a particular state of the application based on a greedy mechanism. The SARSA agent receives a positive reward for executing potentially good events and a negative reward for taking a potentially bad events based on the action value function, which is commonly known as the Q function. The Q value of events is high when the event is never selected and decrease gradually after every selection. The whole process of selecting and execution events will be continuing running and generating test suites for each application. And finally, 10 test suites were generated for each app to obtain more accurate results. Let's move to the objective of this research is to examine the following research questions. The first one is the reduction algorithm with ELBC able to reduce Android suite generated by SARSA? The second one, to what extent does the reduced suite by ELBC maintain the code coverage compared to the original suite generated by SARSA? And the last one, when considering the reduction size and code coverage between ELBC, the current criterion, and EBC, our previous criterion in the previous study, which criterion carries out the best performance? Let's move to the result and findings. ELBC achieved a significant reduction of test suite that were generated via SARSA, ranging from 25.6% to 65.7%. This table presents the size of the original and reduced suite of each Android application using ELBC. The best performance of ELBC in reducing test suite was in Tricky Tripper with an average of 51.6%. This high observed performance might potentially be attributed to the minimal disparity between the minimum and maximum number of elements and test cases across all its 10 test suites. Simple Reminder had the highest test suite reduction, where it became 39 test cases after removing 75 test cases from the original test suite. The potential explanation of the least performance of ELBC in Ankydroid overall, perhaps due to the high average of test case per test suite and the massive number of lines of code. Ankydroid has the biggest test suite with 148 test cases, while the smallest test suite is 94 test cases in TechMate application. Another findings, the vast majority of test suites maintain the original level of code coverage after applying ELBC across the 3 levels involving line, method, and class coverage. This table shows the difference in line, method, and class coverage between the original and the reduced suite, where 0 means there is no change in the code coverage. The reduced suite of simple reminder maintain the same coverage for both method and class as the original. The reduced suite of Kana Quiz and TechMate maintain the same class coverage as the original. A few cases exhibits minor loss in code coverage spanning from 0.01% in the line coverage in Ankydroid to 0.069% in class coverage in Criterion. Comparing between EBC and ELBC, the figure depicts the average reduction of ELBC and EBC for the test suite of each application, and in every scenario across all applications when it comes to the size of reduction, ELBC constantly outperforms EBC, as you can see in this figure. The most significant reduction by ELBC was in Tricky Tripper, as shown in this figure, with an average of 51.6. The chart in this figure depicts a comparison of the average of code coverage in 3 levels encompassing line, methods, and class of the 5 used Android application for the original suite and after applying both criteria, EBC and ELBC. The loose average in code coverage utilizing ELBC is in the blue color bar, is barely notable, ranging from 0.01% to 0.06%, while EBC in the orange color preserve the same code coverage as the original. In conclusion, reinforcement learning is an efficient technique to generate test suite for mobile application. However, there is a room for improvement as these algorithms often produce test suite with redundant coverage. Fine-tuning parameter of reinforcement learning algorithm might help, but this comes with trade-off and requires time-consuming and careful consideration of the characteristic of application under test and its environment. This works take a different approach. Instead of exploring parameter of reinforcement learning, we look at reducing test suite through a hybrid novel approach that combines SARSA-generated test suite with a greedy reduction algorithm based on elements coverage criterion. In all the test suite using the element-based criterion ELBC, which succeed in reducing test suite by 25.6 to 65.7%, with an average of 41.05%. In terms of maintaining code coverage, the test suite reduced by ELBC preserved the same code coverage for the vast majority of the reduced suite, except a few cases with a maximum average 0.06 and minimum average 0.1. Overall, our findings illustrate that ELBC dramatically outperformed EBC in reducing test suite generated by SARSA In case of code coverage, ELBC presented a similar performance to EBC with a slight loose average of 0.03%. Thank you for listening, and if you have any question, just ask. Thank you, and have a good day.